Hi. Today we're going to keep talking. As the title suggests, we're going to put some things together. To get us started, here's a video. Again, watch, record any observations you have.
The main parts of the fire piston are the base, plunger or upper piston, cylinder, and some cotton wool. To use the fire piston, take a small piece of cotton wool and place it in the centre of the base. Place the cylinder over the cotton wool and down to the bottom of the base. Place the plunger at the top and push it down strongly. You'll see that generated fire by heating up the gas inside the cylinder. The fire piston can easily be dismantled. After many uses, soot will be deposited in the base of the piston, and that can be easily cleaned out with cotton wool and then re-lubricated with the sleeve lubricant that's provided. Thank you. I hope you enjoyed watching.
Nice and short. You can buy one of these pistons. But there was fire. That's fun. Same process as before. We're going to go through what changed, what stayed the same. So yes, there was a fire, but I guess what I want to do is I want to zoom in on a certain time frame. We've talked about the idea of T1 versus T2, V1 versus V2, all of those. We're going to say time 1 is just before we press, and time 2 is just when the piston hits the bottom point. The reason I'm saying this is I understand that fire may change the amount of gas, and I'm trying to not overcomplicate this situation. So, in the moments where we're starting with a sealed tube, right? This is actually touching the ends, and we've got our cotton, and then this is time 1, and then time 2 would be where the piston is all the way down, and there's right before this explosion starting to happen. The amount of gas isn't changing. It's constant. However, the person pressed, and obviously the volume changed, and obviously there was sufficient heat to burn the cotton. So the big ones that are changed are pressure and volume. And definitely the thing that we observe is temperature changing in response. I don't think we've talked about 3 variable problems before. But if you want another closer look at this before we get too much into the math side of this, I found a slow motion version, which would totally be fun to watch. So yeah, that would be time 2, and now this is just after. Which, that's insane. Do they slow it down even more? That'd be great. That's just fun to watch. Notice, so the fire starts, there's no spark. The fire starts just because it gets hot enough. So in terms of a particle diagram, I guess we should draw what's going on. Yeah, there's air inside this, right? As soon as we put the top on, there's air. Now, air is diatomic, but forgive me to make things a little bit easier. We're going to draw a bunch of single atom particles just for our, ease of drawing. As we compress this down, like I said, the amount of matter in there is not changing. However, since it's in this smaller space, and because there was a person pressed, that is adding force. That adds a certain amount of energy to the system. So increased pressure yields faster motion. I feel like this would also then yield more force, which could yield more pressure. But that's not really what we observe. What we see is that it yields a more temperature. So there must be something to say, temperature's average kinetic energy. So this, even just this faster motion, we could go back and say pressure, but we can also say increase in temperature. Additionally, because the volume is smaller, I feel like the number of collisions on the wool is going to increase because now there isn't as much space for these particles to occupy and move around in. So the chances, the frequency of collision with the wool goes up. So this also means that volume went down. Now it's hard because we learn that pressure and volume are related. We also learn that volume and temperature are related. It seems like almost pressure and temperature are related. I mean, are all three related? So it's kind of hard to do this in words. I think it's even harder to put this into a graph because we've got three variables, P, V, and T. So I don't think we can do this. I don't think we can do this because both of these aren't showing enough variable. And I don't even know that we can say direct or inverse about any one of them or any two of them. We have to consider all three together. Ideally, we'd want a graph that shows something like, I don't know, 3 dimensions, and there's like pressure, volume, and temperature. But then if you're going to graph that, that's going to be like a, I don't know, like a 3D graph or something. Yeah, something like that. Where the whole surface represents this sample of gas, and a different sample of gas would be a different surface with the same curvature. But that's really hard. Let's talk about the math end of this instead. We know Boyle's law. We know Charles' law. Now here's the thing. In both of those laws, there was that part we don't show, where, at constant amount of gas and temperature, pressure times volume equals pressure times volume. And then at constant pressure, volume over temperature equals volume over temperature. But kind of looking at these two, this shows me if the other thing wasn't constant, what that would show. Like how that would incorporate into this equation. I see the link between the V's here. I think if we put these two together, we can just kind of mush them and we get something that looks like this. I mean, I know there's some questionable, you might be feeling some questionable thoughts about like just combining equations, but it is possible just combine equations because quite honestly, the laws that we see here are derivatives of this combined equation rather than the combined equation being the sum of the original equations that we had, the original laws. I'll show you what we mean. This is called our combined gas law. So called because it, combines pressure, temperature, and volume. And if you're careful about your math, you can back calculate or derive the equations that we saw already, Boyle's law and Charles' law. We said that for Charles' law, is under constant pressure. Well, that would mean that P1 equals P2. That would mean that you can substitute in, right? If P1 equals P2, well, then you can substitute in one for the other. And then if you have the same thing on both sides of the equation, you are allowed to cancel it out. And that's where you get Charles' law. V1 over T1 equals V2 over T2. So in this way, the Charles gas law is really the combined gas law in a specific scenario. That scenario where the pressures are equal is called isobaric. We saw the word barometer before. The bar in isobaric and the bar in barometer both mean pressure. Iso, like isosceles, is same. So isobaric would be same pressure. Talking about Boyle's law, we had said that was under a constant temperature situation. So that would be a case where T1 equals T2. So in much the same way, we can substitute in for the temperatures and then cancel them out. And what we're left with is Boyle's law. So again, Boyle's law is a derivative of this combined gas law. This term would be another iso. This would be isothermal. I know therm kind of means heat, but therm kind of means temperature. The English side of things is a little weird. This suggests a third option that we haven't talked about yet. Right? So on the left we have the pressures are the same. On the bottom we have the temperatures are the same. What if the volumes were the same? let's plug in. And then we could cancel again. And then we get a new gas law here. Again, it's not really a new gas law because it's all a derivative of the previous gas laws that we're seeing in this combined gas law, but it is a new relationship that we might not have directly talked about until now. This is a relationship between temperature and pressure, and you can see that it's got a similar format to Charles' law, so maybe we can kind of back calculate or apply what we've already seen to guess what this relationship is, even though we haven't actually seen it happen yet. First, I should give a name. This one's named after another scientist. This is Gay-Lussac's law. And it's based on pressure and temperature. This term here, where the two volumes are equal, it's isovolumetric. That one doesn't have any funny roots in it. There's just volume is literally right in the word. So, looking at this Gay-Lussac's law, right, we've derived out the constant volume system. Since they're divided, we can apply the same logic that we use with Charles' law, like I said. Whenever we're dividing, we could say it's equal to a constant. Well, if P2 over T2 equals K, P equals T times K. This looks a lot like P equals V times K. That was Charles' law, but we're not doing that right now. But this is the equation of a line, and since there's no y-intercept, it starts at 0. So regardless of what your pressure units are, that might be your line, or that might be your line, or that might be your line. These are for different amounts of gas. But you can always say that pressure and temperature are directly proportional, and their direct proportionality is based on, of course, the Kelvin temperature, just like Charles' law. And you can just see that curve come out. This is another graph of that three-dimensional space surface that we were trying to get at. To try and picture how it works, if you drew any solid lines, you get straight lines for two of them and then a curved line for Boyle's law for the other. But the big thing to walk out with is if there's a situation where somehow the volume is held constant, you can still do mathematical problems to calculate how the change would happen and what you get out of it just by using this Gay-Lussac's law. Now that said, you don't really have to use Boyle's law, Charles' law, Gay-Lussac's law. You could use the combined gas law every single time and just seeing if they mention the word constant, just canceling out that variable. So it's not really about memorizing all of these equations. You could just use the combined gas law every time. Just to show some problems of what this ends up looking like, here are two problems. If you want to do them on your own, of course, hit pause. I'm going to start annotating, figuring out what all these variables are and maybe what equations I want to use, or we should just use the combined gas law every time. So this one has a lot of variables in it. This is going to be a combined gas law for sure. Don't forget that we're in Kelvin. So 5 degrees Celsius is 278. And 24 is 297 Kelvin. So plugging in, when I solve these, I usually just settle the entire left side of the equation, then I'll multiply by 278 and then divide by 400. And so when you do that, your second volume, your final volume equals 0.98 liters. Unfortunately, when you have a combined gas law, it gets really hard to predict whether the volume's going to be larger or smaller or how they're going to change because there's 3 variables instead of 2. You can't just say as pressure goes up, temperature goes up, because the volume part's there too, and that factors in. It turns out in this case that the volume went up. I guess that's because the pressure decrease was proportionally, percentage-wise, more than the temperature decrease, so that kind of makes sense mathematically if you're thinking that way. Here's one more. Do it on your own if you want. That's a pressure, that's a temperature, that's a temperature, and it says pressure. So we could use the combined gas law. Since it says constant volume, though, we can cancel this out and we can simplify our equation. Don't forget, again, we have to convert to Kelvin. And then we get 5.03 atmospheres. This represents an interesting scenario where if you have a sealed container and you heat it, and there's only gas inside, the pressure is going to increase as long as it's rigid. This might sound suspiciously like the videos that we saw at the beginning of this unit. It seems like if you have a rigid container, the volume doesn't change, but the pressure is a function of temperature in that case. But regardless, this should hopefully represent to you an opportunity to either just use the combined gas law every time, or you can think about this and analyze before you start, so you can write a little bit less if you cancel out one or two of your variables. Thanks for watching.